Current, AC, and DC. There are two types of electrical current, DC or direct current, and AC, alternating current. The difference between these currents is how they flow through an electrical circuit. Direct current flows in only one direction through an electrical circuit. An example of direct current is a standard battery. The battery has a set polarity, positive and negative terminals, and will produce an electric current in only one direction. On the other hand, alternating current, as its name implies, flows in both directions. First, it flows in one direction and then it reverses its flow to the opposite direction. See figure 1-16. There are no positive or negative polarity markings in alternating current because the polarity changes so rapidly in the typical AC electrical circuit. The terms cycle and hertz are used to describe how fast the current is alternating or changing direction in the circuit. A 60 cycle AC circuit operating at 60 Hz changes direction 120 times per second. This is the standard for AC in the United States. Conventional current flow versus electron flow theory. Approximately 200 years ago, scientists theorized that electricity had both positive and negative polarities. At the time, they arbitrarily decided that electrical current flowed
from positive to negative.
While it was never actually proven as fact, this theory was accepted for quite some time. This theory is known as the conventional current flow theory. As our knowledge of science progressed, and with the discovery of the atom and semiconductor electronics, it became apparent that the conventional current flow theory was incorrect. It is widely accepted that it is the electrons that actually move, flowing from negative to positive, not from positive to negative. This newer theory is known as the electron flow theory. The emergence of this new theory caused a controversy that still is in existence today. For over 150 years, all circuit designs have been based upon the old conventional current flow theory. Many circuits and devices still used today are based on the conventional theory. This text uses the convention that will make the concepts in each example most easily understood. Most of the figures in this text show electron flow, regardless of which theory is used to explain the phenomena of electronics. The most important point is that the correct polarity must be maintained when building circuits with devices that require a definite polarity. Examine each example for polarity markings. See figure 1-17. Series and parallel. Series and parallel are two important concepts. They must be learned early to fully understand the next few chapters. There are two ways a component can be connected in a circuit, either series or parallel. Figure
1-18
and figure 1-19 illustrate the two types of connections. The circuit in figure 1-18 has three lamps connected to a battery. In this circuit, there is only one path over which the electrons can flow. When the electrons only have one circuit path to flow, that circuit is called a series circuit. The lamps are said to be wired in series with respect to each other. In figure 1-19, there are three lamps connected in parallel. In this circuit, there are three different paths for electrons to follow from battery terminal to battery terminal. Both the series and parallel circuits have advantages and disadvantages. These will be thoroughly covered in later chapters in this text. For now, be able to readily distinguish between the two types of circuits. Fire safety. The possibility of fire is always a threat in an electronics lab or laboratory. When working with electrical circuits, you should have a basic understanding of fire extinguisher types and know how to use them. See figure 1-20. Note, always follow your teacher's instructions concerning the fire procedures in the classroom as well as in the lab area. Be sure to know the location of all fire extinguishers in relation to your classroom, lab, and lab area. Be sure to know the exit procedure in case of a fire. Fire extinguishers are divided into the following 5 classes. Class A includes ordinary materials such as paper, wood, cardboard, and most plastics. Class B includes flammable liquids such as gasoline, kerosene, oil, and common combustible solvents. Class C includes energized electrical equipment, appliances, fuse boxes, and other electrical devices. Class D includes combustible metals such as magnesium, sodium, potassium, and titanium. Class K includes kitchen fires, typically caused by cooking, grease, and oils. Some fire extinguishers are designated with a combination of letters. For example, a fire extinguisher with all of the letters A, B, and C would be suitable for a Class A, B, or C fire. Water extinguishers are only appropriate for Class A fires. Class A uses water or a liquid that reacts violently with the other types of fires, and as a result could cause the fire to spread rather than extinguish. The acronym PASS explains the proper procedure for using the fire extinguisher. PASS, or PASS, was developed to match the recommended procedures by the National Fire Protection Agency, NFPA, for fire extinguisher use. While standing approximately 6 to 8 feet from the fire, you should follow the procedure as outlined. P for pull the pin, A for aim low at the base of the fire, S for squeeze the handles together slowly to discharge the fire extinguisher, S sweep the nozzle from side to side, moving carefully toward the fire while keeping the discharge aimed at the base of the fire. 1.4 Ohm's Law. Electrical circuits that are built correctly will be in perfect electrical balance. The current through the resistance is directly related to the amount of electrical pressure or voltage applied to the circuit. This balance of three factors, voltage, resistance, and current, can be expressed by Ohm's law. Ohm's law is named for the 19th century German scientist George Siemens Ohm. The relationship expressed by Ohm's law is the basic formula that is used more extensively than any other electrical formula you will encounter in your study of electricity and electronics. It is the basis for many of the other formulas and electrical relationships studied in this text. Ohm's law states that the current measured in amperes in a circuit is equal to the applied voltage divided by the resistance. Ohm's law states that the current measured in amperes in a circuit is equal to the applied voltage divided by the resistance. Ohm's law is expressed in three formulas described below. Learning Ohm's law is illustrated in figure 1-21. To see how easy it is to use, simply cover the unknown quantity with your finger, and the remaining letters will show the resultant equation. For example, when the voltage is the unknown quantity, cover the E with your finger, and then I and R remain. Thus, E equals I times R, or voltage equals current times resistance. Now cover the I with your finger, and the E over the R remains. Thus, I equals E divided by R, or current equals voltage divided by resistance. Let's look at an application of Ohm's law. In figure 1-22, a lamp with a resistance of 4 ohms has been connected to a 12-volt source. The current is unknown. By applying Ohm's law, you can determine the current to be equal to 3 amperes. In figure 1-23, a 24-ohm resistance heater works most effectively when using a 5 amp of current. How much voltage is required for the heater to operate at 5 amps? By applying Ohm's law, the amount of electrical pressure needed to conduct 5 amps through a 24-ohm resistance is 120 volts. In figure 1-24, a resistor is connected to a 24-volt source. A meter that measures current indicates there are 3 amperes present in the circuit. Again, by applying Ohm's law, the amount of resistance needed to limit the current value to 3 amperes is found to be 8 ohms. The application of Ohm's law may seem strange at first, but with a little practice it will become second nature to you. Electrical prefixes. Measurement of electrical quantities vary from small amounts to large amounts. To make it easier to label electronic parts and equipment, and to make electronic calculations easier, a system of prefixes is used when expressing electrical quantities. Without this system, we would need to use an excessive amount of zeros to the left and the right of a decimal point. Figure 1-25 is a listing of the most common prefixes used in the electronics industry today. When an electrical quantity, such as a voltage, is written, it is expressed in units such as kilovolt, megavolt, millivolt, microvolt, to avoid using an awkward numerical form. For example, the quantity 5 million volts would be written as 5 MB. If the quantity was 0.005 or 5,000ths of a volt, it would be written as 5 millivolt or 5 small m capital V. It is important to note the use of the uppercase letters and duplicate lowercase letters in these units. When voltage is expressed with a capital letter M, it represents millions volts, but when the voltage is expressed using a lowercase m, it represents the fractional units of thousandths. Summary: matter is anything that occupies space or has mass. Elements are basic or pure forms of matter. Compounds are mixtures or combinations of 2 or more elements. Atoms are the simplest forms of an element, still having the unique characteristics of that element. Molecules are the simplest form of a compound, still having the unique characteristics of that compound. The negatively charged particle of the atom is the electron, and the positively charged particle is the proton. Like charges repel each other, while unlike charges attract each other. Induction occurs when a charged body is brought close to another body. The coulomb is the quantity of electrons, 6.24 times 10 to the 18th power of electrons. Current is the movement of electrons in a conductor. Voltage is the force behind the electrons. It moves them along a conductor, resulting in current. Ohm's law can be stated in three ways. E equals I times R, I equals E divided R, and R equals E divided I. There are two types of current, AC current or alternating current, and DC current or direct current. Correct polarity must be observed when connecting electrical devices. And this is the end of chapter 1.
The Science of Electricity and Electronics. A note from the instructor, Jerome Barnes. Lesson 1. In order to immerse yourself in the field of electricity and electronics, you must first understand the science of electricity and electronics. Matter is anything that occupies space and can be found in various forms, solids, liquids, and gases. Therefore, everything is made of matter. Matter can be described in various ways, but the true identity of a substance is revealed when it is broken down into its purest form. This is known as an element. There are over 100 elements, which are displayed on the periodic table. The smallest form of the element, known as an atom, is most important to the electrical and electronics world. An atom is made up of three important parts: electrons, protons, and neutrons. Electrons are negative, protons are positive, and neutrons are neutral. The nucleus of an atom has an equal amount of protons and neutrons in its inner ring. The outer ring is where the electrons circle around the inner ring. If you add some type of energy, it will cause the atoms to become excited, and the electrons in the outer ring can leave its outer orbit. Electrons that leave the orbit can cause the atom to become ionized or electrically unbalanced. When these electrons leave, it causes the atom to become more positive, a positive ion, because of the greater amount of protons left, greater than the electrons, that is. If the atom gains an electron, it is known as a negative ion, because the electrons are greater than the protons in the atom, that is. The concept of positive and negative charge is the foundational key to electricity and electronics. A good example of this concept is when you take two magnets and put them together. Magnets have two poles, a north and a south pole. In the field, we refer to the north pole as positive and the south pole as negative. If like charges are put together, just negative to negative or positive to positive, they will repel. If opposite charges are put together, negative to positive, they will attract. This force of attraction and repulsion is used to describe the flow of electricity and is known as coulombs. Again, this force of attraction and repulsion is used to describe the flow of electricity and is known as coulombs. These magnets, as the ones shown in figure D, page 1-4, create an electrostatic field where the electrons will flow from the mass with the greater amount to the one with the least amount. Again, the magnets create an electrostatic field where the electrons will flow from the mass with the greater amount to the one with the least amount. This is achieved by simply putting the two magnets together. You won't be able to see it, but you will be able to feel the magnets pushing away or coming together. As they come closer together, you will feel the field strength get stronger. As you push them apart, you will feel the field strength weaken. The materials inside these two magnets are conductors because they conduct electricity. The phenomenon described above was demonstrated utilizing direct contact. Another way to transfer charges is by induction. This is accomplished by bringing a charged object near another. A good example would be using a battery to power a light. Now that we have the basic concept of electrical theory out of the way, let's move forward into learning about electrical circuits. The basic electrical circuit will have three parts. Notice I said basic because as we go further into the course, we'll add more to the circuits, but for now, we will concentrate on the basic circuit. The three main parts are voltage, a load, and a conductor. The voltage, in this case, will be supplied by a battery. The load will be a simple lamp or something we are trying to get to work. The conductor is the wire we use to hook the battery to the lamp or to transfer the current. When you take one side of the battery and wire it to the lamp and wire the other side of the lamp back to the switch and the other side of the switch to the other side of the battery, the electrical energy will cause the lamp to produce light. Always remember the size of your load or lamp in this case, and the source, which is the battery. They are the same. The size of the load and the source are the same. If not, you can cause the circuit to malfunction or not work at all. With the knowledge of a simple circuit, we can now move on to the vital parts of all electrical circuits, which you will see throughout your career in electronics: voltage, current, and resistance. Voltage is the force behind electron flow, or the difference in potential that causes electrons to flow. Its unit of measure is volts, which is expressed by the letters E or V. When voltage is produced, it can either be AC or DC, depending upon the power supply. That's alternating current or direct current. If the power supply is a battery, you will read DC volts. If the power supply is a transformer, you will read AC volts. These types of voltage readings will become clearer to you in the next chapter. Current. Current is the flow or movement of electrons. Its unit of measurement is amperes, which is represented by the letter I. It flows from negative to positive. Like voltage, current has two types, AC and DC. AC, or alternating current, flows in two directions. DC, or direct current, flows in one direction and is usually supplied by a battery. The similarities between the voltage and the current types provide a hint to the type of current it is. If it is DC, the voltage and current will indicate DC. If it is AC, the current and voltage will indicate AC. Resistance is the opposition to the current. It is measured in ohms, which is represented by the Greek letter omega. Resistive values vary among the types of material used to build them. A good piece of material that allows current to flow is known as a conductor. A bad piece of material that doesn't allow current to flow through it is known as an insulator. A good example of both is a piece of wire, see below. The inside consists of the copper piece that allows the current to flow. The outside consists of the material used to cover the wire, and current will not flow through it. Here are a few other examples of conductors and insulators, such as aluminum, iron, steel, copper, rubber, and plastic. Copper is the most widely used conductor in wires throughout the electrical world. Rubber and plastic are the most used insulators. There are only two ways components can be wired in an electrical circuit: series and parallel. Again, there are only two ways components can be wired in an electrical circuit: series and parallel. In a series circuit, figure 1-1.8, the electrons only have one path for current to flow. In a parallel circuit, you have multiple paths for current to flow. There is another type of circuit that combines both series and parallel into one. It is called a combination circuit, see below. As your electronics knowledge increases, you will see this type of circuit has both components. Basic combination circuit, page 1-6, see the figure. As shown above in the figure, if a circuit is built correctly, it will have a perfect electrical balance between current, voltage, and resistance. This balance is known as Ohm's law. See the figure below, page 1-6. Using Ohm's law, if you know the value of any two, the third value can be found. The following symbols are utilized in expressing Ohm's law: E for voltage, I for current, and R for resistance. I recommend that you use a calculator to figure out values in Ohm's law. The best way is to look at the formula shown in the diagram on the left by viewing the horizontal line as a division problem and the vertical line as a multiplication. Use your finger to cover the value that you are solving for. If you want voltage, then the E is covered and it leaves I and R with a vertical line between them. So you multiply I times R, current times resistance, which equals your voltage. If you want to find I, you cover it and it leaves E and R with a horizontal line between them, with E being on top. So you divide E by R, which equals your current. You can do the same for whatever value you are solving for. Take a few minutes and apply some values to different variables to sharpen your skills to get a clear picture of the relationship between the three. Example: if voltage, or E, equals 10 and resistance equals 5, what is I? That would be 2 amps. As we bring the lesson to a close, one other area I want to touch on. In the world of electricity and electronics, you will deal with very small numbers and very large numbers. A prefix system was created to make it easier to deal with such numbers. Shown on the next page, the easy way to remember the prefixes is by thinking in terms of a zero on a number line. If it is to the right, it is going to be represented by a capital letter. If it is to the left, it is going to be represented by a lowercase letter. These letters merely tell you how many zeros go after or before your number. If you want to write 3000, it is written as 3K or 3 kilo. That's K with a capital K. If you want to write 0.003, or 3/1000ths. It is written 3m with a lowercase m. Remembering those prefixes are essential in electronics because they will be around as you dive in deep into the profession.